All right, we're slowly working our way through how to do an analysis of variance. We went through this example looking at P growth, and then I gave you this example looking at the size of ticks on different hosts. And I asked you guys over the weekend to work through this. So who wants to help me walk through this? What's the first step in finding, in calculating the ANOVA? Okay, so we calculated the individual means. So what did you get for each of these? Okay, so like always, what you're going to do is you're going to calculate the sum of each of the values. You're going to divide by the sample size in each of these cases. Now in this case, it's different than the last example in that in this case, the sample size for each sample is different. And so 2978 divided by 8 should be 372.25. 3554 divided by 10 is obviously 354.4. So you have the individual means, the individual sample means for each host, and you have the sample sizes for each of these. What's the next step? Somebody else. Yeah. Okay. Okay, so if we take the mean, subtract the mean from each of these values within host 1, square that, that will give you the sums of squares within. So what did you find for the sum of squares within for host 1? But you just told me how to do it correctly. what do you think you did? What do you think you did? What do you think you did on the homework? You described it correctly to me. What do you think you calculated? Oh, you put it in the wrong value. Okay. Who was operating off of the mean of 372.25? Yeah.
I got for the first one 379.5, 1,274. Is this right?
Mm-hmm.
954.77, and 1,165.
Okay, so these are the sums of squares within. What's the next thing that you need to know? Okay, so the grand mean here is 359.7. I calculated that by just adding up all of those things and dividing by the total sample size, which is 37. Is that what you got? So just take a minute and add these four means together and divide by 4. Just do that really quickly on your calculator in a spreadsheet or something and tell me what you get. $360? Just $360 straight? So this is the grand mean if you just add the mean of sample 1 plus the mean of sample 2 plus the mean of sample 3 plus the mean of sample 4 divided by 4. Why should you not do this? You shouldn't do this because the sample sizes are different. This is a little larger than this is, and it's because this mean is actually smaller than 359.7, but that mean is contributed by 13 observations. And so that will bring down the overall grand mean. If you wanted to operate off of the means, what do you have to do with this? If you wanted to do something with the means to figure out the grand mean, you have to weight them by their sample size. And then you would divide this by what? the total sample size, 37. And if you do that, it should give you the same as you get for the grand mean if you just count up all of those, add up all of those values individually. So you can do it operating off the means, but you have to weight it by the sample size. So the grand mean is either the sum of all the individual x values divided by the total sample size, or it can be the sample size of sample 1 times the mean of sample 1 plus the sample size of 2 times the mean of sample 2 plus the sample size of 3 times the mean of 3 plus the sample size of 4 times the mean of 4. All of that divided by, once again, the total sample size. Either way works, but if you're going to operate off the means, you need to be sure and weight it by the sample size. Why do we need the grand mean? Yeah. Sum squares among. Sums of squares among is this mean minus the sample mean squared. Then what do? Multiply by the sample size. Weight it times the sample size. So you take the mean of sample 1 minus the grand mean squared, multiply times the sample size of sample 1, add that to the sample size of sample 2 times the mean of sample 2 minus the grand mean squared plus sample 3 plus sample 4. Okay? What'd you get? Anybody? So all of these sum squares within sums to 37, 78 in theory. What'd you get for sum squares among? Yeah, Rachel. Okay, and so then we add all those up together, and that should give us 1007.72, right? Or, sorry, 1807.72. Okay, so now we have everything that we need to know. We know what all of our degrees of freedom are because we know what all of our sample sizes are. We know what the sum squares within is, and we know what the sum squares among is, and that's all we actually need to know. What's the degrees of freedom for comparisons among means? Yeah.
It's the number of treatments minus 1.
So number of treatments minus 1, we have 4 treatments, so this should be 3. What's the sums of, well, what's the degrees of freedom for within? Somebody else. It's the total sample size of the whole thing, which is 37, minus what? Minus the number of treatments, which in this case is 4. Symbol would be A, minus 4, so this should be 33. And so you add those together, so the total sums of squares is 36. What is the total, the total degrees of freedom is 36. What is the total degrees of freedom? It's simply the entire sample size minus 1. We have 37 values, so the total sums of squares is 36. Once again, you can always check your math. The degrees of freedom among plus the degrees of freedom within should also always equal the total sample size minus 1. If not, you've done something wrong with calculating degrees of freedom, or you've done something wrong calculating the within sample degrees of freedom. Sums of squares just comes over from the calculations we've already done, 1807.72 and 3778. Those sum to 5585.73. How do we calculate the mean square? Yeah.
It's the sum squared among divided by n minus 1. Or, sorry, the number of treatments minus 1.
Yeah, so it's the sum of squares among divided by the degrees of freedom for among. So 1807.72 divided by 3 should be 602.58. How do we calculate the mean square within?
Some squares of 10
Same thing. Sums of squares within divided by the degrees of freedom within. So that's 3778 divided by 33, which is 114. How do we calculate the F statistic, which is what we actually are testing? Yeah. Yep. You divide the mean squared among by the mean squared within. So this would be 602.58 divided by 114.48, which should be 5.26. Is this what you all got? Okay. Huh?
I'm saying that round.
Yeah, okay, yeah. So rounding error is always an issue. If you're calculating by hand, once again, you should have seen on the test on some of your papers, I didn't have exactly the same answer that you had, and in some papers I mentioned like rounding error because I was following your figures as you went through things. I recognize rounding error. So about this is what you should have gotten. So then how do we figure out what the p-value should be? Well, you can go to an F table, but in the end, we're going to be doing all of this via computer. So let's just go to Daniel Soper's website. If you go to Daniel Soper's website, which you probably are all familiar with now, you can go to the F distribution. So you can search through here, and we can find the p-value calculator for an F test, which is what this is. And when you do that, it's going to ask you for 3 pieces of information. You need the numerator degrees of freedom, you need the denominator degrees of freedom, and you need the value of the F statistic. And so when you put this in here, we have 3 degrees of freedom in the numerator. We have how many degrees of freedom in the denominator? 33. That's the within sample degrees of freedom. And our F statistic is 5.26. And then from this, we can just get the p-value. And in this case, the p-value is 5.957. So this is the probability, this is the observed probability for this data set. This is the observed probability of saying at least 2 of these means are different when in actuality they're not. And so normally we want to be testing at an alpha level of 0.05. This is clearly way lower than that. So we would conclude what about these 4 means? Yeah.
We conclude that our chance of making a type 1 error is very low.
So that's one way of saying it, but reference to these 4 means, what would you say?
We conclude that these 4 means are in fact distinct.
We wouldn't say that all 4 of them are distinct. We would say that at least 2 of them are different. Now, so that's what the F test tests, essentially. This test that we've just run gives us this p-value, and all it tells you is that at least one of these pairs is different. Does it tell you which pair is different? No, it doesn't. It just tells you that somewhere in there, there's a difference. And that's all that it tells you. If the p-value were greater than 0.05, it would tell you that there is not a difference anywhere in there. And so we could look at the means, and we could say, well, this is the highest mean, and this is the lowest mean, so probably those 2 means are different, but this has a huge variance associated with it, so that might make it difficult to see that difference. But just having the F statistic is actually pretty unsatisfying because you don't know which of those means is different from which other means. In order to do that, we have to do what are called post hoc comparisons. A post hoc comparison, what does post hoc mean? For any of you take Latin ever in your past, your checkered history? Yeah.
Does it mean like after the fact?
It means after the fact. It means exactly after the fact. So a post hoc test is a test that you do on your data after you have received information that tells you that there's a difference in there somewhere worth looking at. So you don't do a post hoc comparison unless you have observed a significant overall ANOVA. Imagine that you are trying to think of what a good example would be. Imagine that it's Easter time and you want to go to an Easter egg hunt, and so you go out to a random field and you start hunting for Easter eggs. What are your chances of finding an Easter egg going to be in a random field? What's that? Not good. Why? Because there aren't Easter eggs in just a random field. You're looking for Easter eggs in a place where Easter eggs don't occur. If you want to find Easter eggs, what do you have to do? You have to go to an Easter egg hunt. Why? Well, because somebody has told you that in this field there are going to be Easter eggs. You don't go looking for Easter eggs in a place where Easter eggs don't occur. And actually, fields are the least interesting places to hide Easter eggs. You want something more complex, like a forest. A forest would be a great place to hide Easter eggs. You don't go looking for differences unless something has told you that differences are there to be found. If you get a p-value from your overall ANOVA of 0.09, you don't go looking for other differences because there are no differences to be found. So there's no point in doing post hoc tests. You only do post hoc tests after you have a significant ANOVA, because the significant ANOVA has told you in this field there are differences to be found. Now go find them. Go find the specific differences that are out there, but you don't go looking for those differences until you know that there is a difference out there to be found. Otherwise, you're just wandering around a random field looking for Easter eggs, and there are no Easter eggs to be found. So we conduct post hoc tests after the fact that we have found a significant overall ANOVA. There is a whole body of literature out there written about which post hoc tests perform best under which conditions. There's a long paper written by two guys named Day and Quinn. This Day and Quinn, one of the authors of your textbook is a guy named Quinn, same dude, wrote a long paper in 1989, something like 35 pages in a journal called Ecological Monographs, that is all about what you should do after you observe a significant analysis of variance. It is very long, it is very dry. If you ever do this for a living, I highly recommend that you read that. We're not going to read it, we're just going to take their final conclusions, and we're generally going to do a thing called the Tukey-Kramer test, which I'll show you how you calculate it, but once again, we will never calculate this by hand, but it's easy enough to do in R to calculate this. What the Tukey-Kramer test does is it compares host 1 to host 2, and host 1 to host 3, and host 1 to host 4, and host 2 to 3, and 2 to 4, and 3 to 4. It basically makes all of these comparisons, all these pairwise comparisons. It makes all possible pairwise comparisons, all the while keeping your overall alpha level at 0.05. And so it's pretty much the thing that everybody uses when they do post hoc comparisons. We will get to that in a little while. But the first thing that I want to go through with you before that is talk about what assumptions you have to make in order to do this correctly. And if you violate any of these assumptions, the answer that you get may not be the right answer, okay? But before we do that, do you have any questions on how to actually calculate an ANOVA? Yeah.
I have a question about the p-value. So it has a p-value of 0.09, but at least two then things are similar.
It means that there aren't any differences. So remember, you're testing a null hypothesis, which is that mean of sample 1 is equal to mean of sample 2 is equal to mean of sample 3, which is equal to the mean of sample 4. This is your null hypothesis. Your alternative hypothesis is that, really, it's that any two could be different. So when you find a p-value that is above 0.05, you basically fail to reject this. You basically conclude there's no evidence to say that these things aren't equal. Now, the numbers themselves aren't exactly the same. All you're saying is that you could have drawn all of these means from the same underlying statistical population. You were not drawing these means from separate statistical populations, which is what the alternative is. So a high p-value means there's no evidence to indicate that anything is different. A low p-value indicates something's different, but it doesn't tell you what's different. Okay? Does that make sense? Other questions? Yeah.
0.09, is that just like a number that?
I just pulled that out of my ass. Yeah. No. The number we observed was 0.004. Yeah, this is just a number that I pulled out that's higher than 0.05 to illustrate the other. Yes. Alpha, I've taught you that alpha is the type 1 error rate, but alpha is also the critical p-value. It's the boundary. And if you want to think of it this way as a boundary, it's a boundary for decision making. So if you choose an alpha of 0.05, if you land on this side, there is no difference. And if you land on this side, then there is a difference, whatever the difference is that you're looking at. So it's a boundary. It's a threshold that you cross. That's why people call it a critical value sometimes. You know, I was always referring to the chi-square critical value. It's the value of chi-square, after which you get higher than that, you can say that there are differences somewhere in that distribution. Same thing here. 0.05 is a value that you cross, a threshold that you cross, and once you move across that threshold to small numbers, small p-values on one side, that's indicating that differences are present. If you don't cross that threshold, you basically conclude that there aren't any differences to pay attention to. And so you're always looking at this particular thing as a decision criterion. Now, there's also a whole body of literature out there about using P as a criterion for making decisions. If you have a large enough sample, you will find significant p-values. The reason that you will find significant p-values is that as your sample sizes get really, really large, your degrees of freedom within gets really, really large. So even if there's a lot of variation within each sample, you divide it by a really humongous sample size, this gets really small. When you divide the sums of squares by the degrees of freedom, this gets really small because you have a large sample size. When you then divide that really small thing into whatever size thing this is, that makes a big F statistic, which then leads to a small p-value. And so if you have really, really large sample sizes, you can actually get significant p-values even though the differences that you're detecting are really tiny differences among the means. And this is one of the reasons that some segment of statisticians are like, you shouldn't base statistical decision making on the p-value and the p-value alone. you should also look at what effect sizes you're actually observing, because it's possible to detect with a large enough sample size really tiny differences that actually don't have any real effect. Yeah.
So you're saying as the F statistic goes up, the P statistic goes down?
Yes. Because the F statistic is a measure of how much variation is accounted for by your treatments divided by how much variation is just random variation within your treatments. And so as this gets big and this gets small, this gets big, that means that there's a lot of variation due to treatment, very little variation within treatment, so it becomes very easy to see those differences.
Right, but I'm saying, how does that, like, how does the P value calculate? We just got budgeted it.
Oh yeah. So there's a theoretical F distribution. So I didn't bring my book of statistical tables. So let's go find an F table. So you could get a book of statistical tables, and I think I've mentioned what this would look like, but here it is. So here you have on the top is the numerator degrees of freedom, and down the side is the denominator degrees of freedom. So for us, we would look at 3 degrees of freedom and 33 denominator degrees of freedom, and we would find that we would need to have an F statistic of around, what is that, at 30? Oh, this is the wrong one. This is at alpha 0.05. We need alpha 0.05, not alpha 0.01. So if we go over here to 3 degrees of freedom and 33 degrees of freedom, 2.92 approximately, we could work on the extrapolation if we wanted to. So if F is greater than 2.92, I said, if it's greater than that, then it's significant. It's significantly greater than 0.0. We observed an F statistic of 5.26. That is definitely greater than 2.92. So there's an F distribution out there, a distribution of the F statistic. It's approximately normal, and these deviations from the mean are similar to the T distribution that we were looking at before.
And as that number goes up, the P value goes down.
Yes, because you're further and further out into the fringes of that distribution.
Right. Okay.
Yep. So let's see if we can find an image of the F distribution. It's not normal, it's actually skewed. But what you're looking at is the population of F statistics looks like this, and as you get out into this tail is diminishingly small degrees of the area under the curve as you get out here. And so the critical value for us was at 2.92, and we're out here at like 5.26. We're way out in this tail. So there is an F distribution out there for a particular sample size, and this is drawn on the basis of that. So with all of these statistics, you're always comparing the statistic that you generate to some theoretical distribution of the statistic. In this case, the F statistic has this type of a distribution. And I believe this figure shows you how that is influenced by sample size. As you get bigger and bigger sample sizes, this thing becomes shifted further and further over to the right. So once again, sample size does influence this. But these F tables that you see in textbooks or in books of statistical tables are all based on the theoretical F for a given set of sample sizes. What Daniel Soper's website does is it takes all of that into account and says, okay, you have an F statistic with this degrees of freedom, what would the p-value be based on that distribution? Yep. Which is the same thing that R is going to do for you. Except when you're in R, you don't have to go to Daniel Soper's website. It just spits it out at you. Okay. Other questions as we go along? All right. So when you are looking at data, you have to think about these categories, these treatments, if you will, and and think about where they come from. So there are different types of analysis of variance that you do based on whether the treatments that you have are fixed effects or whether they are random effects. And the difference between this is kind of in how you've chosen the treatments that you're looking at. So a fixed effect refers to you, the researcher, are interested in a particular set of experimental treatments that you are interested in. It's set by the experimenter, and you've chosen them for a particular reason, versus random effects, which are just random samples from a larger population of potential treatment levels. So this is kind of how you would define a fixed effect versus a random effect. But let's think about the two examples that we've done so far. If we go back to this, these are the sizes of ticks on 4 different hosts. Let's say that these are field mice. So you go out into the field, you collect field mice. The first 4 field mice that you stumble across, you collect all the ticks off of them, and you measure how big they are. Would this be a fixed effect or a random effect? Why would you say fixed? Were you interested in that particular host number 1, and that particular host number 2, and that particular host number 3? No, you just randomly got 4 mice, got the ticks off of them, and measured them. You weren't really interested in host 1 as an entity. You're just interested in host 1 because it's a mouse with potentially a tick infestation. In the case of the pea plants, does this seem like a fixed effect or a random effect? Yeah, you could argue maybe that this is a random effect because there are lots of simple sugars that you could have chosen, and then this glucose and fructose would just be random samplings of all of those simple sugars. But the fact of the matter is that they're interested in comparing glucose and fructose to sucrose, which is a combination of glucose and fructose, but bonded together as a compound sugar. So chances are these aren't just it's not a random assemblage of sugars. They had these particular sugars in mind, probably because plants use glucose as an energy source, and plants produce fructose as a byproduct of some metabolic processes. And they are also interested in this difference between a simple sugar mixture and a double sugar. And so one of the ways that you figure out whether you're dealing with a fixed effect or a random effects model is by talking to the person doing the data, who's gathered the data, the person who had the question originally. Because if they're just random selections of a variety of different treatments that are out there, that is a random effect. But if the researcher chose those specific treatment levels because they had particular questions in mind about those, that then makes it a fixed effects model. This changes the analysis subtly. It can change the analysis quantitatively. I always question how much I should tell you about how it changes the calculations. It changes the theoretical calculations, but it doesn't change the calculations that you actually do. So it's something that you don't have to think about in terms of doing the calculations, but it's something that you do have to think about in terms of what the conclusion is, because the conclusion can be altered as a result of it. So know about fixed effects versus random effects in this sense. Many people will treat their work as fixed effects unless there's some evidence to say that they are random. But in reality, when you're actually talking to people about their work, in most cases, people are running random effects types of data, and they don't want to think about fixed effects. They don't want to think about random effects because the expected sums of squares, or the expected mean square rather, gets weirder when you do this. So what we have when we do this, model 1, what we call a model 1, so if you ever see this in any of your reading, a model 1 ANOVA is a fixed effects model where all of the effects are fixed effects. A random 2 model is where a model 2 ANOVA has random effects. And we're not to this yet because we're just doing one-way analysis of variance now, but it's possible that you could have one treatment that is a fixed effects treatment and another treatment that is a random effects treatment. So for example, let's say you wanted to do a two-way analysis of variance. Which we will do after we have spent a sufficient amount of time on a one-way analysis of variance. And let's say that you're interested, for example, in academic performance of students at a college. So this comes to mind because we all are here at a college. Well, you could divide your data up into looking at differences between males versus females as one of your treatments. This treatment would be gender, or sex, depending on whether you're a biologist or a sociologist. And the other thing could be the rank in school. Are you a first year? Are you a second year? Are you a third year? Are you a fourth year? Or are you greater than a fourth year? Are you finishing up your fifth or sixth year? Are these fixed effects or random effects? Okay, explain both.
So I'm saying like for it's random, like who you get within the populations, but you still have to fit them to.
Nope, that's all about random sampling. The question is male and female, is that a random sampling of the possible universe of sexes of individuals, or is that a binary sort of thing? And now we have to think about this differently than maybe we thought about it 2 years ago or 10 years ago. But generally, is male and female a random sample of possible sexes, or is it just the universe of possibilities? Is it a random sample of treatment levels? No, probably not. We wouldn't, as a researcher, we wouldn't think it. We could expand this to include LGBTQ, and we could have all of those categories. I just filled out a survey today, for example. It asked me for my gender preference, and one of the categories was male. There were a lot of other categories in there. If we think about this entire universe, though, and we say, well, we're just really interested in males and females, is that now a fixed or a random effect? That then becomes more of a random effect because we've kind of chosen out of this universe of possibilities these two categories within all of these categories of gender preference. So knowing what's a fixed effect and what's a random effect could be difficult. In terms of one's rank, are you a first year? Are you a second year student? Are you a third year student? Are you a fourth year student? Or are you a fifth or greater year student? Would that be a fixed effect or a random effect? Why fixed? Somebody else. Those are the options, and those are the only options. You could, because this last one is all inclusive, you could be a 21st year student. We actually had a student in biology a number of years ago who graduated, and that the student walked across the stage, but the student never turned in their senior thesis, which is a requirement. In biology, all students are required to do a senior thesis. This particular student did the work, but never turned in the paper and never did the final presentation. And at the end of your 4 years, in April, everybody gets together and everybody presents their research to the Faculty of Biology and Chemistry. And this person never did those last two things. Person didn't do the final presentation, and the person did not do the final paper, didn't turn it in. The person walked across the stage and graduated, but didn't still have a diploma. And on the person's transcript, it would not show an actual graduation date. 7 years later, needs a job. The job requires a college degree. The person comes back and has to present on this stuff that the person hasn't looked at for like 7 years in order to get the stamp of approval of the college saying the person actually graduated, et cetera, et cetera. So this includes that person in this category. Those are all of the possible categories that you could have in terms of one status in college. So this is a fixed effect. Those are all the categories. We didn't randomly select the first year, the second year, the fourth year, and the seventh year. Or in this case, it would have been the 12th year for this particular student. It was weird. It was a weird experience. It was a terrible presentation. Lots of things. Take care of your stuff early. Get it done. Get it finished. This would be a random effects model because what you did was you randomly selected among the possibilities that were there. If you were a biological determinism kind of person, you would say male and female, we are a binary species and those are the only two options, in which case you would say that this is a fixed effect rather than a random effect. If we were interested in performance of males and females at different types of institutions, and so we had university, and we chose some liberal arts colleges. We chose William Jewell College, and we chose Truman, which is a state-sponsored liberal arts college, and we chose, what's another liberal arts college that you guys know about? Oh, Drury. I didn't know that they considered themselves such. We chose those three colleges, and then we wanted to compare ourselves to a Research One institution, so we chose, Clemson and KU and MU and Texas A&M. We've discussed how this could either be fixed or random depending on how you were thinking about this. Within the universities, are liberal arts colleges and R1 institutions the only kind of institutions out there in higher education? No. What are some other examples you can think of? Yeah.
Like technical schools?
Technical schools, so something like Rolla, University of Missouri Rolla. That's definitely a science and technology focused campus. What other kinds of institutions can you think of? Any of you ever hear of Stephen F. Austin State University, my alma mater? What kind of institution would you describe that as? Missouri State would also be categorized in this category. University of Missouri St. Louis would probably be placed in this category. Actually, Stephen F. Austin State University used to be Stephen F. Austin State Teachers College, but these are generally nowadays referred to as regional state schools. And so at SFA, it's in East Texas, it's in Nacogdoches, It has a lot of students that come there from Dallas, Fort Worth area and from Houston, and they migrate to this campus of about 20,000 students in East Texas, Piney Woods. And so it draws regionally from a region of a state. You don't have a lot of people coming from lots of different states. You don't have people coming from lots of different nations. And so it's a regional state school. Yeah.
What's an R1 institution?
It's a Research One institution. It's a big school where they get a lot of money from faculty getting grants and things like this. Their faculty don't teach very much. They have dedicated teachers who do the teaching. The faculty actually do research, et cetera, et cetera. It's all your big schools that you think of. Um, University of Texas at Austin, UCLA, UC Berkeley, all of the big schools would be. This is a Carnegie Institution classification of colleges and universities. If you grew up and live your life in colleges and universities, you kind of know what these are. So the levels themselves are not the entirety of higher education. We have liberal arts colleges and we have R1 institutions. We don't have R2 institutions. We don't have regional state schools, et cetera, et cetera. Some R1 institutions are private. Most R1 institutions are public. But we also don't sample that sampling. We have actually a mixture of both publicly funded and privately funded liberal arts colleges, for example, in this group. This is a random effect because you're not sampling the entirety of that universe. You're not getting some liberal arts colleges, some R1 institutions, some R2 institutions, some regional state colleges and universities. You've randomly selected out of that liberal arts colleges and R1 institutions, which could not be more different from one another in terms of how they do things. So that's the difference between fixed and random effects models. So one thing could be fixed and one thing could be random, in which case you have a Model 3 ANOVA, which is sometimes referred to as a mixed effects model because you have some effects that are fixed and some effects that are random. So let's talk about assumptions. If you had to make assumptions about the assumptions of an analysis of variance, what do you suspect that they would be? What are the assumptions that must be met for you to get a result from an analysis of variance and say that's the right answer? You've seen them all before. The data are independent of one another. Yeah.
Homogeneity of variance.
Who else? Somebody else. Yeah. Sampled randomly. While we're randomly sampling, it would be also be nice if it was also representative, not skewed in any particular way. Random samples can be skewed sometimes. What else? I've already drummed the one that people mention most often, which is the least important one out of your heads. Yeah. These are the four. Nothing new. You've seen this before. So, we already know how to check normality. How do we check normality? Shapiro-Wilk test. What are going to be our raw data for a Shapiro-Wilk test? Here we have a bunch of ticks on mice what are our data for the Shapiro-Wilk test? Let's go back to this. We have host 1, which has a mean up here at 372 approximately. We have host 4, which is at 361. We have host 2 and 3 that are right down here at around 355, right? Host 2 and 3. Let's assume that each of these has a normal distribution around that mean. If we combine all of these data into one big analysis and analyze that to see if it's normal, is it going to appear to be normal? It is. It's going to look like it's trimodal to me if you combine them all into one big analysis. So what should you do instead? You might want to test each one of these independently. So you might want to do a Shapiro-Wilk test on sample 1, Shapiro-Wilk test on sample 2, Shapiro-Wilk test on sample 3, etc., etc. What's the problem with dividing the data up by treatment and doing a bunch of Shapiro-Wilk tests on it? So you might think of it as increasing the error rate, but in this case, you don't really care about whether there are differences among the treatments. You're just testing that particular thing to see if it's normal. So it actually doesn't inflate your type 1 error rate. But if you only have 6 values that you're testing, what are your chances of finding a deviation from normality? Your chances high or your chances low?
Low.
Your chances are low. Why?
Just the way, like, you look at the value, the critical value for your work.
What happens with your ability to determine differences as sample sizes gets low? It's harder and harder to see differences. So you're testing to see whether your data differ from normality. It's easier to detect that difference if you have a lot of observations than if you have very few observations. So if you do a Shapiro-Wilk test on all of these different treatments, host 3, you might find a difference simply because there's more data there than in situation for host number 4 where there's only 6 values. So remember, this is something I talked about when we talked about testing normality that may not have resonated with you at the time, but it should start to resonate with you now. Just because you find that the p-value for a Shapiro-Wilk test is greater than 0.05 doesn't mean that that population is normal. It might just mean that you have a crap sample size and you can't detect a deviation from normality. So there's not a lot of value in doing multiple Shapiro-Wilk tests on a data set like this because each of those are probably going to return a non-significant value simply because you have low sample sizes. So what's a way that you can get around this if you're clever? What is normality testing? Normality is testing the shape of the deviation of the data away from the mean, right? If it's normal, you would expect most of the deviations from the mean to be relatively close to the mean, and you would expect fewer deviations further out from the mean, right? If this one is normally distributed, you would expect most of the deviations to be clustered around the mean and fewer deviations as you moved out away from the mean, right? Same would be true of these two distributions as well. So rather than looking at the raw data, what can we look at? We could graph it, but our eyes are terrible at figuring things like that out. That's why we have statistical tests. If all we could do is look at data and say whether it's different or not, we wouldn't need a class like this, which is good because I'd be out of a job. Graphing is an important way of taking an initial gander at data. It's good to kind of figure out, see if there are outliers and things like that, but you ultimately do have to test it. When we calculate sample variance, how do we go about doing that? You guys all should know this by now. Somebody other than Karis.
We take each table or each value.
I've given you a term that is used to describe what is inside this parentheses. What is that term? Do you guys recall? Not the sums of squares. That's the whole numerator. What's inside is, this is called a residual. If the mean is, if the value is greater than the mean, this residual is positive or negative. It's positive. If the value is lower than the mean, it is positive or negative. This is going to be negative. So the residual values vary from positive residuals to negative residuals, and the magnitude of the residual is determined by what? How far that data point lies from the mean. So one of the things you could do if you were clever, and we are clever in this class, is you can actually just look at the residual value. Don't take the square of the residual, just look at the residual value. What you will have is you will now have a set of distributions that are centered on what would the mean be if in terms of residuals here. Would the mean be 372? What would the mean be? I'm tired of you, Karis. It's fine. It's good. But somebody else. What would the center of this distribution of residuals be? If this was positive residuals above the mean and negative residuals below the mean, what would the mean be in terms of its value? It would be a mean of 0. Good. So this now doesn't become 372. This becomes 0 with some positive residuals and some negative residuals. This mean becomes 0 with some positive residuals and some negative residuals. These two means both become 0 with some positive residuals and some negative residuals. Guess what you have now? You have 37 values of residuals. They're all centered at 0. And they're all presumably on the same scale. So now when you conduct Shapiro-Wilk test, you're not doing a Shapiro-Wilk test on 8 observations, 6 observations, 10 and 13 observations. You're now doing a Shapiro-Wilk test on 37 residuals. Now when you test to see if those residuals are normal around those means, and you see that you have a p-value greater than 5, what can you rest a little easier about? You now have a sample size of 37, and you do a normality test, and you find that the data are not different from normal. What do you feel good or bad about? Yeah.
It's one of your assumptions that you need to have.
Yeah, if you have 37 observations and you see that you don't deviate from normality, you feel much better about concluding that you don't deviate from normality than if you reach that same p-value with only 8 observations or 6 observations. You're like, oh, I did a Shapiro-Wilk test on 37 residuals. It shows me that I'm not different from normality. I'm way more likely to take that result as a true and accurate result rather than when I did it on only 6 values. So what we will typically do is we collect the residuals from all of the treatment levels, combine that into one big test of normality, test that to see if it's normal, and then that's what we base all of the rest of our work on. Simply because we have more statistical power to do that test. Once again, you'll see this throughout the literature. People do this all the time because if you really care about the normality assumption, you want to test the normality assumption realistically rather than in some bogus fake way. Like, well, it says not different from normal. What's your sample size? 3. Well, duh, of course it's not significantly different from normal. You got 0 statistical power for asking that question. Different from normality? What's your sample size? 50? Okay, I'll believe that. Sample size is crucial. You should always be thinking about the sample size underlying anybody's conclusion. What do you notice about these data when you look at the sample sizes and where the means lie? You have ticks that are big on a particular mouse. Why might those ticks be big? Yeah.
Bigger mouse?
Might be a bigger mouse. They don't report mouse data on here. Why else might they be big? Could be the ticks have been there for a while. Think about sample size though. Why might these 8 ticks or these 6 ticks be on the big size and these 10 ticks or 13 ticks be on the smaller size? Think of yourself at the, what's the name of that buffet? Why can I not remember? The Golden Corral. Here at the Golden Corral, it's 10:30 in the morning. They just opened up. You walk in, you're the only person there. What do you have all to yourself? You have the Golden Corral all to yourself. What can you do? You can eat to your heart's content. Because you got the whole Golden Corral all to yourself. Go to the Golden Corral at 5:30. Who's at the Golden Corral at 5:30? Everybody in particular. What group is there at 5:30? Oh, that's very cruel of you to say. They're there for the early bird special. Now you're there at the Golden Corral, and there are a bunch of old people there at the Golden Corral. And have you ever seen old people at the Golden Corral? They're fierce. It is a competition to get to the banana pudding before it's all gone. A bunch of people at the Golden Corral, what do you have to do? You have to divide up the fixings at the Golden Corral among all of you. If you're there at 10:30 in the morning when they just open up for lunch, you got all the Golden Corral to yourself. Maybe these ticks are all big because there's only 8 of them feeding on that one mouse. Maybe these ticks are all big because there's only 6 of them feeding on that one mouse. Maybe these ticks are smaller because there's 10 and 13 feeding on that one mouse. Wouldn't it be nicer to have a bigger sample size to determine whether or not these means are actually true? Sample size is important because sample sizes that are low could be non-representative, and they could be non-representative in ways that make means look like they're not different, and low sample sizes could also be non-representative in ways that make it look like things are different. So sample size is important. You should always be thinking about sample size. That's how you test the third of these assumptions, the normality test. You take the residuals. The last assumption, which is the assumption of equal variances, we'll pick that up at the beginning of class on Wednesday. By the way, for those of you planning your getaways, no class on Friday. So we'll meet in class on Wednesday, and I will not be here on Friday. You guys can be here on Friday if you want, but it'll be without me.